So this lower bound and upper bound procedure I propose, remember, it's there to help you figure out if your answer turned out reasonable or not. I really don't want people stressing out about it. The points are, let's do something quick. So just like a single multiplication, height times width, and let's be reasonably accurate, but we don't have to be super duper accurate. So here's an example of a time not to stress out. How about the integral from 0 to pi of sine t plus cosine t dt? It looks like this. What about a lower bound? Well, 0 is not a quick lower bound because the function has values less than 0. We could draw a box of negative height and width pi, but it's just not worth it. What we could do is look at this graph and say, overall, it looks like there's more positive area than there is negative area, so I'm pretty sure the answer is going to be positive, and we're done with the lower bound. For an upper bound, we might wonder what value is right here and draw our upper bound box according to that. Here we go. And it's about 1.4-ish. And you do not need to get super high precision on that. It's actually square root of 2, 1.414, blah, blah, blah. But the upper bound, our true integral value is not going to be near that anyway, so 1.4 versus 1.414 just doesn't matter. So just go with a quick answer like 1.4 times pi. That's good enough. And in particular, do not take the maximum value by finding where the derivative is equal to 0. It's not mathematically wrong, it's just a massive not good use of your time because it takes too long and it's error prone. It's fine to just graph it, say there's the max. Desmos even puts a point there for you. You can copy down the number. So it's not meant to be an exercise in calculus to do the upper bound and lower bound. It's meant to be an exercise in setting up guardrails real quick, and they don't have to be too exact. You're hoping to not get anywhere near the guardrails anyway, right? Okay, the other thing to talk about is what about the plus c? We said before we're not going to bother with it, and let's see whether that actually works out or not. So let's do the integral 0 to 1 x squared dx. It's our favorite parabola here. We found on a version that was flipped left-right that the area was 1/3. The area is still 1/3. So go ahead and write the antiderivative with the plus c, and then do the bracket thing from 0 to 1. So we'd say 1/3 x cubed plus c, bracket from 0 to 1. And so that would be 1/3 1 cubed plus c minus 1/3 0 cubed plus c. When you plug in the 0 and the 1, and what's going to happen there? You're going to get 1/3 plus c minus 0 minus c, and the c's are going to cancel, and you get the 1/3. So did we need to find out what c was? Did we even need to write c, or do you think this canceling is going to happen every single time? It always happens, so that's why we're just not bothering writing the plus c or figuring out what the plus c is. So I'll say that always happens. So don't bother to write the plus c when we're doing definite integral problems, because it'll just end up canceling out.